So this video is just going to be an overview of survival analysis. There's going to be two other videos after this. One's going to talk about Kaplan-Meier survival functions, and the other's going to talk about Cox proportional hazard regression. But this one's just going to cover some of the basics around what an incidence is and what time to event data looks like, so I won't have to spend the introduction of those other two videos covering that. I'm hoping to just kind of lay this groundwork before. So for my Kaplan-Meier video and Cox proportional hazard model video, I can just kind of get right into it. Survival analysis is also called time to event analysis, and that's just kind of a more accurate description because the outcome isn't necessarily always survival. Some of the things you might be interested in are survival, so time to mortality following treatment, or it doesn't even need to involve people. It can be time until the failure of some mechanical part. It's common in engineering to use survival analysis. Or it can be time until pregnancy or a variety of other things. Basically, the structure is a cohort study where you have this calculation of the time spent in the study for each individual until some event, and it's kind of similar to Poisson regression in that way that you're accounting for time and typically using data from a cohort study. So like I said, the major measure of disease frequency for survival analysis is incidence, and there's two major types of incidence: cumulative incidence and incidence density. And I'm just going to compare and contrast the two here. So cumulative incidence is the number of events occurring over the follow-up over the number that were at risk at the start. And incidence density has the same numerator, the amount of events happening over the follow-up time, although the denominator is person time at risk. So in addition to taking into account the number of people, like cumulative incidence density also takes into account the amount of time they spent at risk. So there's no time in the denominator for cumulative incidence, while incidence density does have time in the denominator. So this changes its interpretation, where cumulative incidence is a proportion, goes from 0 to 1, and there's no time in the denominator, so it can also be called a risk. Well, incidence density is a true rate in the sense that there's time in the denominator and it has units, it's number of events per time, and it can exceed 1. So the reason that we don't need to take time into account for cumulative incidence is because it's assumed that everyone is followed for the same amount of time and that follow-up is complete for everyone. While in incidence density, we're able to account for the fact that follow-up is incomplete for some by not just counting the number of people, but the amount of time each person spent in the study. So this is kind of related to what I just said, where cumulative incidence is best for closed populations. That means no one's being added or lost over time. While incidence density is better for open populations where people are able to be added and lost throughout. And cumulative incidence, there's no individual information on how long anyone was followed, but incidence density does have that. Okay, so that was a lot, but those are just some things to keep in mind going forward. So like I said, cumulative incidence is the number of events over the follow-up period over the number at risk at the start, and everyone is followed for the same amount of time. Here we have 4 people followed for 4 years. 2 people did not have the event and 2 people did. This is a closed population because everyone was observed for the whole time, no one dropped out, and no one was added late. So there's 4 people at risk, so that's what we have as our denominator. There was 2 events that occurred at some point over the follow-up time. I know I put it here at the end, but it didn't necessarily have to happen on year 4. 2 events happened at some point over the 4 years, and for 2 people the event didn't occur. So that's everything we need to find cumulative incidence. It's the number of events over the follow-up period over the number at risk. So it's cumulative incidence of 0.5. So this is just another way to look at survival data, where here we have the number at risk, 100 people started in the study, and we have these intervals where we're following up for 5 years, And at each interval, there's some people who didn't show up or had the event is a better way to say it. So on year one, there were there were 100 people alive after year one. I guess no one died in that. And it got lower every time. We were able to record the number of events only at these intervals. And once observation ended at year 5, there were 12 people left. So a big problem with this way of looking at kind of interval measures is that we know that 36 people had the event, whether it's a death, in this time period, but we don't know exactly when. It might have been 3 years and a few months. It might have been 3 years and like 8 months or 9 months. We don't know. We just know it happened sometime in this time period. So using this information to find cumulative incidence, we can do the number of events over the number at risk at the start. So since there were 12 people alive after 5 years, we know that 88 died in total. So there were 88 events and 100 at the start, so a cumulative incidence of 0.88. So some of the major limitations of representing survival analysis this way are that it doesn't permit censoring. So these dips are assumed all to be events. We're not able to account for if any of those were censored observations. And also it doesn't use exact times. Whenever an event happens in this interval, we don't exactly know whether it happened early or late. So a way of finding cumulative incidence that accounts for these two things is Kaplan-Meier survivorship, where the first thing you'll notice is that these horizontal lines aren't all the same length, and that's because every time an event occurs, that's when these dips are happening. So at each of these dips, we're able to calculate the probability of an event. So at time 1, we take the number of events that happened here, the size of the decrease, over the number of people that were eligible to have the event, and we're able to find the instantaneous probability of the event at time 1, and we can do that for each of the times. And this dash here is how we represent censoring, and censoring is able to be accounted for by accounting for the fact that that this person wasn't at risk. Basically, we're able to account for censoring in our calculation of the probability of the event at time 3. So we're able to find cumulative incidence from this through a few steps. So like I said before, the probability of the event at time 1 is number of events at time 1 over the number at risk. So it kind of looks like we had 100 people at risk and 10 events. So let's say that's true. We have the probability of the event of 0.1 at time 1. And we can find the probability of the event at these other times. And the probability of survival at each of these times is just the complement of the probability of the event. So probability of the event at time 1 was 0.1. So we know that the probability of survival was 0.9. And we can do that for each of these 3 times up to time 3. And to find the cumulative probability of surviving up to time 3, we can use this multiplication rule, where whenever there's multiple things that have a probability and each of them has to occur, we can find the cumulative probability of each of these 3 things happening by multiplying them. So because we are able to do that, we're able to find a cumulative probability of surviving up to time 3 of 0.67. And you'll note that since each of these is less than 1, the more time points we have, the smaller the probability of survival will become. And the complement of this cumulative probability of survival is the cumulative incidence. So that's how we're able to find that with Kaplan-Meier. Kaplan-Meier is also able to plot separate lines for those that are in the exposure negative and exposure positive group. So we're able to have a bivariate analysis here for our survival time, and we're able to use methods to figure out whether these lines are significantly different, and that's something I'll cover in my Kaplan-Meier video. Also, we're able to stratify by confounders. Say we thought the lines would be different among males and females, we can do a stratified analysis. And in this way, it's really analogous to like this 2x2 table. We have fatty diet and liver disease. That's kind of like our bivariate analysis here, and we're also able to stratify by alcohol consumption, kind of like we did here um, with males and females. So in that way, Kaplan-Meier is kind of like the bivariate analysis of survivor analysis. So even with some of the advantages of Kaplan-Meier, there's still some problems. We're not able to control for multiple confounders the way we can in a lot of regression techniques. And also it's not using incidence density, which has some serious advantages, incidence density, that I'm going to get to soon. So yeah, just kind of reviewing the main differences. Incidence density is more of a rate that accounts for really accounts very well for censoring because we're able to calculate the amount of time that each person contributed. It's good for open populations, people coming and going, and you're able to get a rate. So censoring is something I've talked about a lot, but just to kind of more explicitly mention what it is. So right censoring is when individuals have their follow-up stopped before the end of the follow-up time, not necessarily because they had an event like this person, and that could be because they stopped showing up to the appointments, they were lost follow-up, they might have died of something other than the disease of interest, or they might have not gotten the disease by the end of the follow-up period. Left censoring, on the other hand, is when people are recruited at various points. So they're contributing different amounts of time to the study, but not because they dropped out early, but because they started later. And with those two types of censoring, this is more what time to event data typically looks like, where this is an open population, people are being added over time and people are dropping out earlier. And you'll notice that here, this is a function of calendar time, where we can also standardize it based on follow-up time, where this is the exact same data here, but instead of calendar time, we just have the amount of time they were followed up. And you can do the same by standardizing at the end rather than the beginning, same data. If you want to take into account both survival time and calendar time, you're able to do this thing called a Lexis plot, where here we have both the calendar time that the person started, or sorry, we have when the person began being followed, and we also have their survival time. So survival time will have the same units as calendar time here, but we're able to also account for when they started the study, where if we're worried that there might be systematic differences in risk over calendar time, we're able to stratify by that. Also, we're able to account for whether someone was exposed or not, so we can have an exposure positive and negative group for our time to event. And this kind of brings me to how time to event data is structured. So typically you have their exposure status, the number of years followed, and whether they were stopped, whether their follow-up was stopped because of censoring or because of an event. So person 1 here was followed, they were exposed, they were in the exposure positive group, they were followed for 1 year, and they were stopped, their follow-up was stopped because they were censored. Person 2, they were in the exposure negative group. They were followed for 2 years, and their follow-up stopped because they had the event. So they're censor negative. So that's basically the way that this data can go from being visual into a table format that could be analyzed. So incidence density has some serious advantages. It allows censoring, which is much more realistic. You can stratify by time and confounders, multiple ones, and you can account for a time-varying exposure status. So I'm going to go through each of those things. So some of the major assumptions for incidence density is that dropouts are at random. So those who drop out aren't dropping out for a reason that's systematic, like if they're somehow dropping out because they're getting sicker and stop showing up to appointments because they're unable to. Also, losses occur uniformly over intervals, if there are interval measures, and also there's no systematic changes in risk over calendar time. So the way we're able to calculate incidence density, it's the number of events over person years of observation. So here we have 4 people. This person followed for a year, this person for 2 years, 2 years for this person, and again 2 years for this person, for a total of 7 years contributed. And we had 2 events, so we have 2 events over 7 person years. Comes out to 0.29 events per person year. So our first assumption, like I said, is there's no differential loss to follow-up, where we want to be able to say that this person didn't they didn't leave the study for a reason that's related to the exposure or outcome. It happened at random. Also, assumption 2 is that there's no systematic differences in risk over calendar time, where we want to be able to say that the year this person contributed is equivalent to this year contributed by this person and this other year. And yeah, basically that would be a problem if this person started in year 3 and year 3 was somehow different. If there's somehow effect modification by time, that would need to be taken into account. Also, the third major assumption is there's an equivalence of the person year structures. So if we have 5 person years, we want to be able to say that the risk is the same for 5 people followed for 1 year versus 1 person followed for 5 years, which both represent 5 person years. And this can be problematic for certain diseases, like lung cancer and smoking. If one person's followed for 30 years, the risk that person is going to get lung cancer is pretty different from 30 people followed for 1 year, just because of the latency between smoking and lung cancer. How we can address these 2 assumptions, both whether the follow-up over time systematically differs between like 5 people followed for 1 year or 1 person followed for 5 years, and also this difference by calendar time. We're able to investigate and control that effect by standardizing by calendar time, basically, and month of follow-up. We're able to look at these 2 things differently and analyze the rate separately by calendar time or by follow-up time, and we're able to determine whether there's systematic differences in risk. We're also able to stratify by things we think might be confounders, where here we're showing the analysis separately for males and females. And we can stratify by age in addition to calendar time and follow-up time, where here we have a separate analysis for those in their 20s, 30s, 40s, and 50s. And that brings me to one of the more complex parts of this, where if we're controlling for age, calendar time, and we're looking at survival time, we have 3 measures of time here. And I was originally going to try and make this into a 3D plot where this is the y-axis, x-axis, and this axis is coming out as like a third one. But that looked too complicated. So I basically took this third axis and just plotted it separately here. We have the same 4 individuals, and this is their survival time as a function of their age. And this is their survival time as a function of the calendar year. And what this would permit us to do is have an analysis that's both stratified by calendar year. So let's just say we think that there might be some difference in risk before 2000 and after, and we think there also might be some difference in risk among those under 45 and older. So we can stratify the analysis by these 2 separate time points. So this green person, they had an event, and we know 2 things about the event. We know the event happened before 2000, and we also know they were under 45 when they had the event. So their event gets contributed to the before 2000 strata and the under 45 substrata. We also know they contributed about 5 years, and we know that all of those 5 years happened before 2000, and all of them happened before the age of 45. So their 5 person years gets contributed to this strata and substrata. The blue person had their event at after the year 2000 and older than 45 years of age here. And this is a little more complicated. They were in the study for 20 years, and 10 of those years happened before 2000, and the other half of their follow-up, the other 10 years, happened after the year 2000. And similarly, the first 10 years of follow-up happened before the age of 45. So 45 is here, and that's half their follow-up. The other half happened after 45. So they contributed 10 years to this before 2000 and before 45 strata, and another 10 years to the after 2000, older than 45 strata. The yellow person had an event, and it happened when they were, it was after the year 2000, and they were older than 45. So they contribute a event to this over 2000 strata and over 45 substrata. Oh, and yeah, they had, similar to before, they were in the study for 10 years. 5 of those years happened before 2000. In those same 5 years, it was before the age of 45. So they added 5 years to this strata and substrata. And their last 5 years was after the year 2000 and over the age of 45. So they contributed an additional 5 years to this. The red person had no event, but they contributed 10 years, and all of it was before the year 2000, and all of it was over the age of 45. So we're able to find a rate both stratified by whether it was before 2000 or after, and stratified by age. You'll notice here that we didn't have enough data to find a rate for each of these combinations. In the real world, you'd have way more than 4 people, so it would be likely that you'd be able to calculate the rate. And you're able to see if risk varies as a function of calendar time or age. Another cool thing about using incidence density is that you can permit exposure status to change over time. We're looking at smokers and non-smokers, where smokers are the green ones and non-smokers are the blue ones, where this person ended up quitting smoking and contributed some time into both groups, and this person took up smoking, also contributing some time to both groups. One potential problem is that you need to ultimately attribute their outcome to either their exposed time or unexposed time. And what we typically do is assign their event status to their exposure status when the event occurred. So this person had the event, and even though they spent some time as a smoker, they're considered a non-smoker who had the event. And this can be kind of problematic depending on what the outcome is. But the major assumption here is that their time as a smoker has no bearing on their current event status, so there's no carryover. And there's certain situations where that might be true, where they were a smoker, didn't have the event, and if it's some outcome where now that they're a non-smoker, they're in the clear, it's only an event that can happen while you're a smoker, that would make sense. But it could be an issue if we're looking at something like lung cancer, where here this would be considered a non-smoker who had lung cancer. And it might be this time previously they spent as a smoker. Say they were a smoker up until this like very moment, and then they died as a non-smoker or got lung cancer as a non-smoker. This way of doing it would completely disregard all this time spent as a smoker, which could be a problem. Cumulative probability is another important concept as long as we're talking about survival functions. So it's the probability of survival plotted against time, and you start out with a high probability of survival, but as time goes on, the odds of surviving almost goes to 0. This is a smooth version of what I talked about with Kaplan-Meier, where we have the number at risk and the probability of the event at time 1 and time 2, and the probability of survival being 1 minus this probability of event. And because the probability of survival at each of these times, say this is probability of survival at time 1 is like 0.9, and then at time 2 it's 0.8. These are all less than 1, so you're multiplying things together that are less than 1. So as more time points are added, you're multiplying by more things less than one, to the point that this survival function is getting smaller and smaller, almost to the point that survival probability is almost zero at this point. A related idea is hazard, and hazard's the probability of an event happening at time t, given that it hasn't happened up to time t. So it's a conditional probability that, given that someone survived this long, what are the odds that the event's going to happen in this next little span of time? And this is the foundation of Cox regression. I'm going to talk a lot more about hazard in the Cox proportional hazard video. But just briefly, the Cox model has, just disregard this one, I'll talk about it more next time. We have the person's hazard being a function of this baseline hazard multiplied by the increased hazard as a result of these covariates, so like maybe the treatment and these like age and other things. So in summary, survival analysis measures time to an event, and it lets us use incidence as a measure of frequency. Cumulative incidence, its major player here is Kaplan-Meier, and it's like a bivariate analysis that allows controlling of one confounder at a time. The more complex measure of incidence is incidence density. Its major player is Cox proportional hazard regression, and this is a multivariate regression like logistic regression or Poisson regression that lets you handle multiple confounders at once.